Thanks so much for coming. STARFAIR 0, first one. A lot of y'all know what the Makerspace is, but a lot of y'all don't know what the Makerspace is, so we're going to talk about that. What is Starforge? We're next door. I hope you saw the shop. If not, we have tours later. But we're a College Station Makerspace. We're set up as a nonprofit. And a Makerspace is just it's a place with tools, equipment, space, stuff to make stuff. We have a lot of members that just like making stuff, and they don't have to own all the tools themselves, so we provide all that tools. But more than just a location, it's kind of a community of makers. A lot of people here are people that use our space, a lot of people that are part of our community, and it's actually really amazing what some of the awesome things our people have made. Now, it's kind of fun, the story, so I'm going to tell a story of how we got here before we get started. So, it started with, why do we exist? Forgot about this slide. In College Station, there's a lot of people that like to make stuff. They want to have the tools, the space, the equipment to make the stuff, but there's nowhere that does have it. Students don't have access to anything like that. And so we saw a need for it in the market, and we filled it. So Starforge just fulfills the space where people can build cool stuff, basically. Yeah. So, like all good things in life, it all started with a really sketchy rocket engine. Ismail was working on, where's Ismail at? Over there. He was working on this rocket engine in high school and came to college and wanted to work on it here, but he didn't have anywhere to do it. So he rented a little tiny storage unit, like 100 square feet storage unit, which sounds like a lot, but it's not. We had this rocket engine. You could see it outside. Afterwards, you can go check it out. But we were working on it there. It was just not enough space. That's actually how we met. He barged into my dorm room one night and said, hey, work on a rocket engine with me. And I said, okay. But he wrote a blog post about this rocket engine and said, look what we did with no money and no space. What if we had a little bit of money and a little bit of space? And then we got some donations and started Starforge. Our first iteration was called Space Zero. It was a 400 square foot storage unit with 2 wallets. Now we filled it up. We started buying tools and equipment. We started buying shelves and tables and stuff. And we very, very quickly completely filled it up. Not a great photo, but completely full. You could barely even walk around at that point. We tripped the breaker a couple times. We're like, this has got to change. We need someplace new. So we started looking, and we found our current location, which is right there, which is called Space. Oh, we also had a little flyer. As you can see, it was always a plan for it to be a larger makerspace later on, and then we found the larger makerspace, which we call Space 1, which is just really just Starforge now. So early February 2023, that's about a year and a half ago, we moved into our current space. You can see, it took some time to get it filled up. You can't see anything in that video, but we had to rip the floor out. It was a lot of work. But it was about 2,000 square feet. It's everything we wanted and more. We opened shop, we started buying more tools, we started expanding, and we didn't have any more like huge, drastic leaps after that. We did have gradual steps, a little more here, a little more there, until we ended up where we are today, which is our current location. Now we have a nice 3D printing lab, shop in the back. We have a very nice wood shop. We have an electronics lab. It's all nice and clean next door, so afterwards you can go check it out. But we're currently at over 130 members. We have all sorts of people working on all sorts of stuff, and we really have done some awesome things. There's some more, there's our electronics lab. We have a little hangout corner where we can do some homework and whatnot. Cool, and so that's Starforge. I mean, we're around, we have, I think, around 10 staff members now. It's all volunteer work. None of us getting paid for this. We just do it because we love it, and it's amazing. I'm really just so glad we get to do this. Anyways, welcome to STARFAIR. We figured we should have some sort of project showcase. People have been working on stuff all semester, all year. We want them to be able to show it off. So welcome to STARFAIR. Have a nice little agenda. First up, we're going to have a couple just quick project talks. First up from Yasha's talking about his kind of robot arm project. Next up, Brandon talking about his DIY one wheel. And then Ismail's going to close it out with kind of a how to run a successful little project. After that concludes, we will have a quick intermission, and then we'll have tables over there. A lot of people here have tables prepared. They'll just go, staff, you can go drop by, say hi, check out the cool projects. We do have water in the back if you get thirsty. And yeah, besides that, after these talks are done, we'll also be doing just rolling tours at Starforge next door. Just go out the door, take a right, you'll find it. You can come check the shop out. So, without further ado, please get up for Yashis.
Howdy. Howdy. Nice to meet y'all. I'm Yashis. I'm currently a master's student here at A&M, and I'm the founder of a little company. Today I'll be giving a talk on my project that I'm doing for both my master's thesis as well as my company, and the talk is titled Predicting the Future, and you'll see why in a second. So going back to why I got interested in robotics, and this talk will be about my robot arm and how I predict the future to teach it. So going back to how I got into it, early on, I, like everyone else, thought that robots were really cool, but also that they're really expensive. These are some of the robots that I've had the pleasure of working with over the years. As I've done research, you can see the Spot robot dog, some robot arms there, as well as a robot boat that we use for search and rescue. And the common theme among all of these is that yes, they're really capable, but they're also exceedingly expensive. Each one of these robots is on the low end, at least $10,000 to $15,000, and that's if you're getting a real good bargain, and that's meant to be affordable. So this generally is not super accessible for people who want to innovate, and a broke college student who wants to mess around with robots for fun. So I started building my own. As an undergraduate student, I started participating in hackathons, and I started out by building this small robot that was a Braille printer. This was for a hackathon project where it basically took a little pen nib and indented onto paper to make greeting cards for people who were blind so that they could have keepsakes from the people that they cared about and they could read them in Braille. Next, I started building CNC machines to start making parts out of aluminum and wood to make robots in the future. Then I realized that this one was super terrible and couldn't actually do that much for me. So instead I used it to make a much bigger CNC machine, which I kept in my bathroom for a few years. And then afterwards, I then made a few other machines. This is a robot that I made for research that's intended to go into rubble piles and provide companionship to trapped victims so that they can improve their outcomes and kind of have companionship until they get rescued. And this is finally the robot arm that I made. And the reason I did all of this is my ultimate goal was to have a robot butler. I think it would be super cool to be able to have a robot that I can just ask it to make me a drink or go get me a beer or something, and it'll just go roll over, grab it, and then come back, make me toast or coffee in the morning. So I did. Meet Alfred. Alfred is named after the butler from Batman, and this is Alfred. He moves around on a wheeled robot base at the bottom, and then you can kind of see up top there's a robot arm and a screen and some other cameras and sensors up top, and he rolls around, and the idea is that he can roll around and he has one robot arm that he can grab stuff and manipulate with. But the hard part is that humans are really complicated. It turns out that it's really difficult to make robots do anything complicated that a human can. We just do a lot behind the scenes with vision, and we kind of inherently know how to grab things, and that's really hard to teach to robots. So I pivoted. As I started to discover that hardware wasn't really the hard part, it was the software and teaching robots how to do things that was the hard part. I both pivoted my company from making those robot arms, as well as pivoting my thesis, which was previously focused on disaster robotics, towards this sort of manipulation-based research on how do we teach robots to do things for us. And I made this pivot back in around November, and I'm supposed to graduate in May. So that left me with about 4 to 5 months to effectively teach a robot that had the intelligence of a newborn how to perform advanced manipulation tasks. So I had my work a little cut out for me. So I sat down and I got acquainted with 2 of my very close friends for the next few months, coffee and textbooks, and I got to work. And what I found out very soon after reading papers and textbooks is that robots by themselves, and even after humans teach them, are really dumb. And even at the highest levels of research, it's still hard to make them do anything useful. So what do you need to do in order to effectively be able to tell a robot, can you make me toast? Or can you pick this up and put this over here? Even simple tasks like that require a lot of training. So what do you need to do for that? You, 1, need to recognize all of the things around you, the things that you're going to manipulate with, the things you're going to move, where you need to move to. You then need to associate what things that you've recognized and where they are. You then need to track those things as either you move throughout the world or those objects move. You then need to predict what happens next. And intuitively, this is sort of what you do as you learn a new task, is you learn how things are supposed to be done and what it's supposed to look like, and you kind of have that mental model in your head, and then you then try to replicate that as best as possible. You then react accordingly based on your mental model of the world and what that prediction of the world should look like. And then you try to match that, I guess, prediction as best you can to get your task done. So I'll break down each of these steps and how I got that done with my robot. So steps 1 and 2 is recognizing what's around you. So the way that we do this right now is we basically take in a whole bunch of these pictures and label it with everything that's inside of the picture. So here you see in the left side image, you see that the data is a picture of an image, and you feed in everything that's in the image, the living room, the dog, the blanket. But at this point, the model that we train, the brain, only can take in the image and give you everything that's in the image. It doesn't really know where those are. So then you need to take another step of feeding in a smaller image of exactly one thing and one label of like, this is what a blanket looks like, this is what a pillow looks like. And if you combine these two, you get the result to the right, where if you feed in a picture, it'll tell you what things are inside of it and also where they are. So now we've solved the step of, okay, we know where the things are that we want to work with, but what do we do with them? We then need to know where those things go throughout time. And here you see a little GIF of if we want to track all of the ducks as they cross the road, you see that we basically feed it through. And this is again done by a lot of data of saying, here's where this thing is, here's where that same thing is in the next frame or the next like part of the video. And you do that over and over again until you have like a machine learning model or a brain per se that can track these things through time. Next, the hardest part is that once we know where things are and once we're able to track these things throughout time, the hard part is predicting the future, which is building that mental model of the robot for once you have a certain task, for say, pick up one block and put it on top of another, what that's supposed to look like. So we want to keep important information about what we're manipulating or what we're handling, because that informs how we handle it. Per se, you would pick up a plate differently than you would pick up a mug, and that sort of information is really important, and it needs to be encoded into the brain of the robot, kind of like it's encoded into our brain. So you see that this is this is the raw picture of what the robot sees, and to the left you see what the output should look like. So I guess the ground truth prediction, like what the world looks like in the next state. And then to the right you see what the robot predicts. So you can generally see with enough data, you can get that prediction to actually be pretty close. So you see there's not a lot of difference between those two as it goes through. So now that you have the predictions for like a really rough prediction of like in vague shapes of what the world should look like in the next part of the video or the world state, you then want to make the future happen. So the way that you go about doing this is you take what you see currently and you compute like a movement that you need to make on the robot to make the two pictures of what you see currently and what the prediction looks like match as closely as possible. And then you then predict the future again at that step, and then you move and then you predict again. So if you do that, you can see that to the left, you see a little animation of what that looks like. So it's thinking right now, predicting the next frame, and then it moves and then drops it. So that was when I gave it a task description of put the apple in the dish rack. And that's all I gave it, and it had access to the camera, and it just went ahead and did it. And while this seems rudimentary, these are the fundamental building blocks of what are going to enable robots like this to perform much more complex tasks in the future, like building machines for us in the future, cooking our food, and generally getting to robot butler level. And you can see that this is not actually super far off from where even companies are. Some of you might have seen this demo. This is from a company called Figure that has a humanoid robot, and they fundamentally kind of do the same thing. Here they're kind of asking it what it should do with the cup, and it tells itself that it needs to put it in the dish rack, and it really does that. And this is also done with a lot of data, but this brings us to our next steps of what's next now that we have this very simple model of like, we can put the cup in the dish rack or the apple in the box or whatever. What's next to get to a robot butler level? One is to collect a lot more data. Humans have collected data on how they interact with the world since the second that they're born. And it's really difficult to teach a robot for years and years and years how to do all of the things that humans do 24/7. And we fundamentally understand the world differently and in more depth than a robot can if it doesn't have that data. So one step is to collect more data, and the second step is also making it easier to use more data. Because right now, what you have to do to train the system is basically take a fake version of the robot and then move it through and then perform all of these tasks manually and then label all of what's going on, and then it'll learn how to do those things over and over again. So whenever you tell it to do it, it can do it by itself. But that's not necessarily going to scale up well in the future because you don't want to have people demonstrating on every type of robot. The goal is eventually you can just take videos on tutorials on how people do things on YouTube and have the robot learn from that. So the goal then is to make it easier to use more data of YouTube videos, a person wearing a GoPro, of other robots performing the same task, until eventually we can collect this large amount of data and information that we humans learn throughout time to eventually get to a robot butler. And that's been my work. Thank you. I'm gonna I'm going to hand it over to Brandon to talk about his one wheel.
Howdy, I'm Brandon, and I'm going to talk to you about this one wheel that I built at Starforge Foundry right next door. Let's go next. So this is, I call it the hover wheel because one wheel is trademarked and I don't want lawyers coming after me. So this is a hover wheel. It's right there in front of you. So what is a one wheel? The one wheel is a self-balancing electric skateboard. So it has a single wheel in the center and you can lean left or right to move it on. So whenever I hop on it, I lean left or right. It's not going to turn on. And I would go one way or the other to try to keep me level. So where do you start whenever you go on a project like this? Do you look at the frame? Do you look at the foot pads? Do you look at the battery? Or do you even start writing the software for it? Well, there's a giant wheel on it. Why don't we start at the wheel? Everything's built around it. So the motor requirements, it has to be low cost. I'm a broke college student. I can't be spending a ton of money on this. It needs to be easy to get because if I need to get something custom, price goes up and it negates our first point. It has to have lots of torque to support me so I don't fall over whenever I'm trying to ride it. So can anyone think of anything that balances humans and is super cheap? How about a hoverboard? So I bought a hoverboard off of Facebook Marketplace. You can see they're pretty cheap. Numbers are a little blurry, but I bought a super cheap hoverboard off of Facebook Marketplace, took it apart, and then started researching how can I take these motors that I have and putting them together into a one wheel. So I did some research on Google, and it turns out someone has already done this project before. They made this motor right here on the right. It's super high torque because we're using hoverboard motors. It's low cost, only costs about $125 to build just the wheel. And it fits a standard go-kart tire, so I can get this super cheaply online, and I don't have to worry about getting a custom tire fit for it. So does it work whenever you put it together? No, it does not work. So this thing does not actually fit together. Whenever I first printed it out, it was about 40 hours of printing, and it didn't work the first time. So you can see, probably not really well in this picture, but the case does not fit around the wheels very well. And so I had to go into CAD and make some modifications to it so it would fit. So it turned out my motors were slightly bigger than what the other person used when they made it. And I put the whole new wheel together, 3D printed some new parts of Starforge, and there was my wheel. And that was probably last October. So I had a couple more things that I had to do. So then I started working on the frame and design. So this was in my computer. I designed all of this. I built the rails. I built the foot pads that needed to be there. And then started 3D printing more parts of it. And eventually I got to something that looked like this. You can see it looks pretty close to the CAD model that I had. And so then for the foot pads, we need to figure out, is the rider actually standing on it? So I need to detect weight somehow. And the way I did that is there's this material called Velostat. And there's this material called Velostat. And it changes how much electricity can go through it based on how much weight is on it. And so I put 2 wires under it. I put the grip tape on the top that my foot actually sits on, and based on how much weight goes across it, it allows more or less electricity to go between those 2 wires, and I'm able to detect that with the controller inside the board. So now we need to figure out how can we actually control the motors inside of the wheel. And so it turns out that when you buy a hoverboard, you get the control electronics with it. And so it already has 2 motor controllers in it because there's 2 separate wheels. And it has the ability to take input from various sensors and compute an output. So I tried using that, and it turns out that the output of a hoverboard is not similar to a one wheel. Crazy. So it turns out some really smart people online wrote new firmware for this board here that allows you to make your own calculations on a separate board and then send over how much motor power they want to this board here. And so whenever I did all that, I found out that, hey, it doesn't balance whenever I just plug motors into it. So I have to make a controller that can do those balance calculations. They have an Arduino library. So Arduino is this programming language used to program microcontrollers. And so it turns out I know Arduino. So this is really nice, and it worked out really well. So whenever I bought the hoverboard, it came with a free Arduino in it that is actually used for doing the balancing calculations on a real hoverboard. So I wrote new software for this to do all of my balancing calculations. That was signal processing, control theory, electrical engineering to get all of these systems to work together. And it was a lot of boring math that took me a couple months to figure out. And then, so after 3 months of programming, we have a success. And so there's my first time riding right outside the front there. And we go down the Harry's entrance. And so there were some huge issues with V1. I rode the board for about a month and a half before stuff started to break. There are some really hard problems to fix in software that you really hard to reproduce and find what is causing those problems because I don't have very easy control over the software. The setting changes are hard. So anytime I wanted to change a setting on the board, I had to take the entire board apart and re-upload code to it just to get a setting change. So it was probably about 2 minutes to make a change every time I wanted to. And so the footpad was also unreliable. There's some fun stories from Starforge where I got on the board, I was testing it, I got off of it, and the board just did not turn off. So it shot out the front door of Starforge into the parking lot, and me and Ismail were chasing after it, going about 14 miles an hour. So I made a new controller. So this is a printed circuit board that I manufactured actually with Yashis, who was building the robot arm. He had a machine that can make these. And so we built this little PCB one night, and that allowed me to have a phone app that I can actually control the settings on the board and see my battery voltage and speed. I'll show you a screenshot of that in a second. It's super easy to update the code now because I can go into the settings and just make a couple changes. And the board also has the ability to have code uploaded to it without taking the entire board apart. It does it all wirelessly. And so then I'm also able to adjust the footpad sensitivity. So we fixed that big problem last time of it shooting out the front door of Starforge. And I can adjust how sensitive it is and make it more sensitive if it's not detecting my weight. So this was the app that I built. So on the right there, that's my watch app. So I have an Apple Watch, and I was able to make a bunch of graphs on my watch to check my speed and battery voltage while I'm riding. On the left there, that's the settings pages to change all the different values to adjust how it balances. And eventually, we got to work, but please do not try to replicate this project. There were multiple software and hardware issues. I fell on university because one of my motor wires unplugged randomly, so I got pretty hurt from that. It's not waterproof, so yesterday you guys all saw how it was pretty rainy out. That thing would not have survived. I rode it through the rain once, took it back into Starforge, took it apart, and found a cup of water sitting in my electronics compartment. It turns out, luckily, I put conformal coating that made it somewhat waterproof, but it's not good to have a cup of water sitting around in your expensive electronics bay. I did not save any money with this versus buying a used one wheel. So there's one over there that I bought after, and that was the same price as building that one. But hey, yeah, it was about $450 to build that one. I bought that one for $500, so it was not much of a difference. It also took me 150 hours to build this over the span of last semester at Starforge. And if I paid myself minimum wage, I would have made $1,200 off the project. But hey, it's a learning experience. So I learned a lot from this project and taught me a bunch about stuff. So if you want to check out the code and the CAD, if you're into that type of stuff, it's on GitHub. You can take a picture of this now, or just ask me for the link later after the presentations. So yeah.
Great job, kiddo. Howdy, everyone. I'm Ismail. Where's the clicker? I have the clicker. Thanks, bro. All right. Howdy, everyone. As I just mentioned, I'm Ismail. I'm one of the co-founders of Starforge. I want to shout out to these guys. Boise is a freshman, by the way. So imagine what he's going to do when he's a senior. So. All right, so my talk today is going to be about something I've wanted to talk about for a while now, is how do you build great hardware? I have some very strong opinions about this. These are things that I didn't come up with, but these are things that we've seen happen in Starforge over the past year, things that we noticed worked well, things that we noticed did not work so well. And without further ado, let's get rolling. So why should you even build hardware? Well, quite frankly, it's a lot of fun. Yeah, it's fun. Like, that's all. It is the best way to learn engineering. Like, The kind of stuff he did cannot be taught in class. You have to go and do something like that to get those kinds of skills. And that's like extremely valuable. Like SpaceX and all of these top companies, they're known to hire people from SAE teams, SRT teams, that kind of thing, because these guys have hands-on experience. This is directly exactly the same thing. So this is really how you get those skills of being like an extremely good engineer. You are gonna have a great time. Some of my favorite times were over this last week. We're just chasing after the go-karts that ASME built. And sometimes things break, wheels shear, drivetrains snap, boo-hoo, we fix it, but we have a great time along the way. You will make some truly fantastic and epic friends. All of us running Starforge, hanging around Starforge, we're all best friends. We wouldn't have met otherwise. So you should build hardware. You'll have a great time and you'll learn a lot. All right. What should you build? So a lot of people come in, they're like, hey, Ismail, I love the shop, man, but I just don't have ideas. Just don't. And I never really had a good answer, but after thinking about it, here's what I came up with. So you should build something that excites you. A lot of the reason why hardware is really cool is because you can use it to make other people's lives better. Whether that's yours or other people, it doesn't matter. But to build something that's really good, you have to put in a lot of work. It's not easy to do what these guys have done. So you have to really do something that is exciting to you. So just think, what got you into engineering? What got you into building things? That kind of thing is maybe what you should try to focus on building. So build something that you would think about in the shower, because like Paul Graham once said, nothing great ever gets built without being thought of in the shower. So yeah. If you can't think of something off the top of your head, that's fine. Think about something you would have loved to see as a kid. Or if you're still coming up blank, go talk to your friends and family. A lot of these great projects, you do them with friends. So, gather around your best buddies and try to think of something. I bet you'll come up with something. There's probably that one idea or that truck y'all wanted to build and it never happened, and now's probably the time to do it. But it's okay. Let's see. It doesn't have to be expensive. Look, you guys, he doesn't have much money, all right? But he still can build stuff, Just set aside however much money you're comfortable setting aside. I promise you'll get it back. Every dollar I've spent on rockets and miscellaneous other weird things that don't work has come back to me. I promise you. It comes back in the form of skills and things that you learn over time. So don't fret too much about the money. Just also know it doesn't have to be super expensive. You can build something for like $10 that is really cool. All right, let's go. Gather the homies. Listen, you're building a team here, all right? You can't work with people that you don't trust. If you guys don't trust each other, you're not gonna get great work done, okay? Very, very important to be picky about your people. Work with people that you like, because you're gonna be spending a lot of time with these people. So if you don't like them, don't work with them, all right? This isn't school. We don't force you to work with people, okay? So gather your friends. Try to keep your team small. I beg you, please. I know if you're doing something super complicated, it might seem like you need to recruit all of the smartest people. I made that mistake once. It wasn't fun. What winds up happening is all of the knowledge gets spread out between you, and you sometimes you lose responsibility for who does what and who made what decision, and it overall winds up being less productive than if you and like 2 or 3 of your friends did it with just a really small team. So less is more here, I promise. You can do a whole lot more than you would think. So like for example, he taught himself control theory in the past month or 2. You can just do that, Rocket science, control theory, robots, LED cube matrix thingies. You can just teach yourself anything pretty much. We have the internet now. You want to designate responsible engineers. I want to be able to point at him and be like, listen, you are responsible for this part. It's extremely useful. It pays huge dividends at the end of it. And responsibility is great. Avoid subteams. It's really useful to just, avoid subteams. And the reason I say that is because you would think there's a lot of work, but a lot of times there isn't. And so what winds up happening is the team lead winds up doing 80% of the work, and then leaves the other rest of the team members to do 20% of the grunt work. Not a great time. Try to avoid it. And then avoid remote work for hardware. So a lot of what we're going to talk about next is like testing and manufacturing, and like it's a whole cycle. Like it's very tightly bundled. And so you want to try to avoid remote work here for hardware. I did it once. It was more painful than it was worth, let me tell you. But it did get us here. So stuff to do on day one. Figure out what you're going to build. This should not take too long. Figure out how much money you're willing to spend and where you're going to get that money. And then who's responsible for what? Point fingers. Be explicit. All right? It saves you some pain later on. And then give yourself a deadline. Something I noticed, which is really funny, is the past week has been way busier than the rest of the month. I wonder why. It's because we have this event. Everyone's rushing to finish their stuff so they can show it off. So give yourself a deadline. It's really helpful, more helpful than you'd expect. And yeah. All right, start researching. So like we see, you can pretty much teach yourself anything you want. We now have a truly great series of resources. I personally read Wikipedia on a daily basis. It's extremely useful. If I'm ever curious about a subject and I don't know the first thing about it, the very first thing I do is I read Wikipedia. Wikipedia is going to basically give you a very broad overview of the subject, and then it'll give you reference material at the very bottom. If you're doing like super math heavy, super physics heavy stuff, it's a good starting point. Not the best, but it's good enough. YouTube, a lot of really niche hardware subjects are online, like how do you weld, how do you use an oxyacetylene torch, how do you do like design for these kinds of things. There's countless dozens of lots of resources on YouTube. Look at examples. So, like when I built my rocket, I looked at examples from like rocket teams that did it was that one lander challenge. Anyways, the X Prize, that's what it was. I referenced a lot of their materials. I referenced people I knew who were building similar things. You can just reach out to people and they'll answer your questions. One thing I did, which was extremely beneficial when I was building my rocket, was I reached out to a friend of a friend who became my close mentor over the past couple of years in high school. His name was Ken Mason, and he basically taught me everything about rockets. And a lot of times you'll realize that people who've done this and who've done what you want to do, they're so incredibly happy to share what they know. You just ask, be nice and polite and considerate of their time, and they will gladly help you. You'd be surprised how far you can get with just smiling and nodding. You want to learn just enough to build V1. It's really tempting to go down rabbit holes, but rabbit holes are deep. There's a reason they're called rabbit holes. So you want to just learn enough to get the first thing just working. And you want to move fast. It's really important that you move fast. So yeah, you don't want to end up like this guy. So, all right, design phase. So I know it's really tempting to just go to hop into CAD. So you should avoid that. You should basically try to figure out what materials you're going to make it out of. Use materials that you can easily get, like steel that you can buy locally. Specifically find where you're going to buy it, how much it's going to cost. You should have a very good estimate of how much your project is going to cost before you ever go into your CAD program. For those of you who aren't sure, CAD is computer-aided design. It's like Google Docs on steroids for us, McMaster has a lot of really well designed 3D models that you can use. So I don't do much very organic CAD anymore. Just start simple. Build out the very core features first, and then add features as they go on. I promise you, it's a lot. Sometimes the basics take a while to get working. Get hardware ASAP. For example, say you have a 6-week project. You want to have hardware on the very second week because you need to be building and design, and you need to be testing immediately. So there's an iteration cycle, and it gives you time to test and remake your parts. So say your parts break, which they will break. Something is gonna go wrong. Something is not gonna get assembled according to plan. Guess what we were doing at 3 a.m. last night? Assembling the rover. But yeah, a lot of fun, great times. So you should really give yourself time and space to remake and rework parts, redesign parts. It's gonna happen sooner or later. You should iterate quickly and cheaply. So for example, if you have a budget of $2,000, I highly suggest you not spend $1,900 on your very first prototype. You're gonna be broke. But yeah, so keep it simple, start simple, build out your core features, and you have to test as you go. So if you're building a go-kart, try to test your engine. Of course, if you have a new engine, you know what's gonna work and what's not gonna work. Sometimes, you have an iteration and it goes sideways. You have an idea that didn't go as well as it should have. Scrap it and start over. Just design your program for your parts to be really cheap and easily replaceable. Yeah, so like we said, V1's probably gonna break. Just make peace with it. It's perfectly fine. It's not shameful if your parts break or explode or fail catastrophically, as long as they don't hurt you majorly. A couple bruises are fine. But yeah, so this was the rocket engine. That was an ESP32 for a robot I was working on last semester. One really important distinction. Sometimes it might seem like we're wanton with safety. We take safety very seriously. There's a huge distinction between hardware safety and human safety. I do not care if your hardware blows up. What I care about is people getting hurt. Your priorities should be the same. So understand how your parts are going to fail. If you're testing a rocket engine, you should have a large failure zone. But it's perfectly fine if your project breaks. That's not a big deal. And have fun, This is supposed to be fun. You're supposed to have a grand old time with the homies building stuff. So yeah, fix issues together. And then, it's perfectly okay for you to build something entirely just because it's funny. And I think that's it. Thank you. I'm going to hand it off to Michael.
There we go. Hey, so that's it for our talks. Thank you so much. Now is the fun part where you get to go see all the cool projects people have made. Before that though, let's talk about the future real quick. In case y'all haven't heard, this whole building complex is getting torn down maybe in December this year, which does mean we're gonna have to move if we want to survive. We're hoping to survive because we don't want to die, obviously. But what that does mean is we're gonna have to change some things up. And that means things are gonna be more expensive, honestly. And we're doing really well right now with our current space. We've done all this on a shoestring budget run by a bunch of volunteers that are full-time students. However, we're gonna have to change. We're gonna need some help. So if you like what you see, if you like what we've done here, please reach out to us. I think my number's on the next slide. Reach out to us, come talk to us. Any of us that give talks, we're all staff here. And let us know. We'd love any sorts of help, any sort of support. We are a nonprofit, so it's all tax deductible. But besides that, y'all are free to go. We'll have our tables. Yeah, enjoy. Thank you so much for coming.